Hello, everyone. How are you doing? So let me start with a question. What if I told you that this object in my hand, that this object could be the key to unlocking large-scale fault tolerance? That it's a qubit, or in fact that it's many qubits, and that these qubits are 100,000 times more efficient than the technology that our biggest competitor is working with. Hold that question, hold that in mind. I'm going to come back to it shortly. But let me start by telling you a bit about Quandela. So, Quandela is a French startup founded in 2017. Our headquarters is about 25 kilometers from here in the Paris region. We have 130 people today working at Quandela, with some very senior scientists, and tomorrow morning you'll have the great fortune of being able to see Professor Pascal Senelard delivering the keynote speech. And we are a full-stack quantum computing provider. That means that we look after hardware manufacturing in our fabrication facility, where this device comes from, that we look after assembly and integration of quantum processors in our factory space, that's our second production facility, but also that we look after the full software and middleware stack, that we develop quantum algorithms, and that we make all of this available through the Quandela cloud. Now, I'm going to talk about the roadmap for scaling, but what I want to stress here is that I'm not just theorizing. We deliver hardware. So today, Quandela ships photonic QPUs. We deploy cloud access, and we integrate applications. And everything that we learn and everything that we build today, it feeds into our scalable fault tolerance roadmap. So the message that I want you to keep in mind is that I'm not going to be just talking about a hypothetical architecture. Everything I talk about is part of a platform that exists, that's living, and that's evolving fast. So today's QPUs, they're built around three main module types. And we have single-photon emitters to generate our photons, which become our qubits. We have quantum interconnects, which allow us to route those photons. And then we have control and readout, which is performed with integrated photonics. So we program these integrated photonic circuits. We have very fast clock rates. We build up statistics. And our algorithms and applications are built around this architecture today. But we're not just scaling, we're scaling smart. And so that means that tomorrow's devices, they're built with exactly the same modules. Everything is modular. You see the same photon emitters, the same quantum interconnects, and the same integrated photonic circuitry. You just see them in greater numbers, all interconnected by optical fibers, and of course with higher performances, so that we can reach error correction thresholds. So our goal is to deliver utility as soon as possible, and to build a future that's realistically fault tolerant, so that we achieve fault tolerance at a realistic scale. Now I want to step back and kind of explain some of these extraordinary claims that I started out by making. You're going to hear a lot in these next 2 days about different quantum computing technologies. I think we can divide qubits into two broad families. On the one hand, you've got matter qubits, and these are things like superconducting qubits, atoms, ions, etc. And on the other hand, you have light qubits, and those are the photons. In a sense, these are kind of the two modalities in physics. It's the two sides of the famous Einstein E equals mc squared equation. And you can do quantum computing either with matter or with light. And your decision to work with matter or light is going to impact on the advantages and the challenges that you face. So to put it simply, if you're working with matter qubits, you can generate entanglement by getting your qubits to interact. But the very fact that your qubits interact with each other, that means that they're susceptible to interacting also with their environment, with everything around them. And that's a problem. So when they interact with the environment, they leak, their quantum state starts to leak and deteriorate through a process called quantum decoherence. And this is very detrimental. So this is the biggest challenge that you face if you work with matter qubits. On the other hand, if you're working with light qubits, the story is radically different. A photon in a transparent medium is not going to lose its state. Decoherence isn't really an issue. But for that same reason, it's difficult to make the photons interact with each other. And so the difficulty in photonic quantum computing is inefficient operations. You can get them to interact, but the operations are what we call probabilistic. You know when they work, but they only work a very small fraction of the time. So if you look at this, it might strike you. It struck us. Wouldn't it be great if you could have the best of both worlds? If you could work with light qubits and you could have all this lightweight scalability and speed, but you could also have the matter qubits for the efficient entangling operations, the stability, the memory. So maybe there's a solution. And that brings me back to this device that I started out from showing you. So I'm going to go through some pictures so that you can see, because I think in the audience you're going to have difficulty making out what's in my hand. Typically it's packaged with a fiber on the top. Our photons come out of that fiber. But if we peel back the packaging a little bit, what you see is a microchip. And if you zoom into the microchip, you would actually make out little microstructures, what we call micropillars. And zooming in further into those micropillars, each one of them is home to a quantum dot. And this is where the magic really happens. So a quantum dot is a fascinating object. To make things simple, we'll say that a quantum dot is a two-level system. You can put it into an excited state by shining a laser on it, and it's going to relax back to a ground state, but in doing so it will emit a photon. So it's a perfect emitter of single photons. It's a very efficient emitter. And that's what we saw in these diagrams as the single photon emitter module. But it's actually much more than that. It's a hybrid technology, because that quantum dot, it has a spin. And that spin can be up or down, and allows us to treat the quantum dot as a qubit in its own right. And so what we have here is a matter qubit, which is emitting photonic qubits. And it's emitting them on demand. On demand is very important, because if you work with fully photonic technologies, that emission step is probabilistic. It's very inefficient. Here we have a very efficient solution. It's even better than that, however. It actually creates entanglement on demand as well. So remember I said entangling gates are inefficient operations if you work with photonics. Now we've found a solution to that bottleneck. And that's because when the quantum dot emits a photon, the polarization of the photon is entangled with the spin of the quantum dot. So it allows us to generate these entanglement links at the generation step. What we have here is a best of both worlds solution. It's a natural light-matter interface. We're combining the best of photonics and the best of matter qubits. And this is the key to scaling efficiently. Now, there are a number of scientific papers that we've put out detailing our advancement on this. I think if you want to see the state of the art, and it's really been very exciting what we've achieved over the course of the last year, the keynote talk tomorrow morning from my colleague, Professor Pascal Senlar, will go into much more detail on that. Okay, so what does it mean? We talked about efficient operations and not. We've got a deterministic source of photons. If you work with fully photonic technologies, how does it compare? Well, I told you the operations are inefficient. If your photon generators are inefficient, the solution that you have to take is to parallelize. You need very many of them to make sure that a small fraction actually produce photons when you ask for them. But more than that, you're going to need to check where the photons were created, and you're going to need to route the photons to where you need them for the next step in your computation. All of this is a massive overhead in the number of components. The story gets worse when you want entanglement. So entangling operations are also inefficient, and that means you're going to waste very many photons. So you're going to have lots of components to build each photon. You try to entangle them. Only a fraction of the time does it succeed, so you're going to have to parallelize more and more components and have bigger and bigger switching networks. The number of components explodes. Now that's a qualitative explanation, kind of an intuition for why the hybrid approach gives a huge resource advantage, but I think it's very telling when you take a concrete example and you work through the actual numbers. And so what we've done is we've benchmarked on our competitors' architecture. Fully photonic approaches propose to achieve fault tolerance through what's known as fusion-based quantum computing, FPQC. That approach to quantum computing relies on generating intermediate-sized entangled states. These are the kind of spider web image that you see in the top right. These states need to be generated in great quantity, and afterwards you fuse them together and you perform error correction. But first you need those states. And we crunched the numbers on what the resources required are to build those states with our hybrid technologies or with fully photonic technologies. So we have a patented approach with our hybrid technology, which works with 12 sources and with a very modest number of linear optical components. When you go through on the pure photonic side, lower bounds for what you need are 1.6 million sources, and even more of each of those linear optical components. This is quite dramatic. This is a 100,000 time resource efficiency advantage. It's difficult to understate how powerful that really is. But that's when we play by our competitors' rules. That's when we use their architecture. And actually, it's much more interesting for us to work with a native architecture, which is tailored to our hybrid technology. And that architecture is the spin-optical quantum computing scheme. And that scheme uses, again, the same modules, the spin-photon emitters, quantum interconnects, and small linear optical components. In this scheme, the spins of the quantum dots are the qubits that we're doing our computations with, and the photons, they serve to mediate entangling gates between those spins. It's a highly versatile architecture, which is very important because it allows us to leverage the best error correction codes. It allows us to really stay on top of the best emerging state-of-the-art in error correction, which is a field which advances very fast. Now, we've calculated the error correction thresholds. First of all, we started with the most vanilla error correcting code, the surface code. But within a year, we also released thresholds and analyses using more advanced codes. We came up with techniques which reduced the number of emitters that we need by removing check qubits. And we moved to dynamic codes, which gave us better thresholds, in fact, doubling our loss threshold, which is the key metric. You're going to hear more about the spin coherence time tomorrow morning in Pascal Senelar's keynote presentation. But just to say that it's very valuable to have a versatile architecture. The other reason why the spin-optical approach is key is because it's always going to give the best error correction thresholds, and that's due to having the shortest optical path. The main difficulty with photons is that they're going to get lost. Once you've overcome the inefficient operations, your main difficulty is losing photons. Here we've got a very small number of optical components that each photon sees from generation to detection. I mean, you can basically count them. It's emitted, it's routed, it's filtered, it passes through some linear optical components, it's coupled to a detector, and it's detected. You know, this is a small number of things that need to be optimized. We avoid complex multiplexing and fusion networks, and that means that we have the highest loss tolerance per component. It's the most achievable approach. All right, now I'm going to just very rapidly say a few things about fault-tolerant quantum computing, because I think it needs a bit of a rethink. You're going to hear many people Mickey swinging this week, saying, I have the biggest number of qubits. The point here is not all qubits are equal. And I just want to give an illustration of this. And I've taken public roadmaps from some leading companies in matter qubits to make the comparison with fair extrapolations about where they claim they're going to get to and the state of the art in error correction. So you see that some of them are claiming more qubits than us. Actually, I'm being even harsh on myself here. When I talk about our number of qubits, I'm really talking about the number of spins. These devices are so efficient that a single one of them powers an entire NISQ machine today. But I'm thinking in the long term, so I'm going to talk about just the spin qubits. And here you can see it looks like, OK, Quandela has less qubits than the others. But it's not the raw qubit numbers that matter. A first point is that what you really care about for fault tolerance are the logical qubits. How many logical qubits do your physical qubits buy you? And connectivity is key, because that allows you access to the best error correcting codes. So already, when you take this into account, what codes are accessible to these technologies, you start to see a difference in the number of qubits, the logical qubits that are available. But it goes even further than that, because is not enough to have a logical qubit, which is just a proof of concept on which people do a single logical operation. If you want to do something useful, you're going to need to be able to accumulate thousands of gates. So you're going to need a realistic target error rate. And that's going to bring you a bigger fault tolerance overhead. And there, the difference starts to become dramatic. And you can see that our hybrid approach starts to take off. I've put in a curved line, some reasonable expectations for advances in error correction over the coming years. But even without that, you see a striking difference. And there's a third point that I really want to stress, because this one is very understated, and it's logical clock rate. All right? So what I'm counting here is the clock rate for an error correction cycle. So let's say parity check measurements between your qubits. When you work with the hybrid approach, your limit is essentially how fast your classical electronics can keep up. If you're working with matter qubits, you may be in a different scenario. You may actually have to physically move qubits around, for example. And you can see there's a very big difference. Now, just hypothetically, I take numbers from roadmaps. I take error-correcting codes of reasonable sizes to achieve key applications of fault-tolerant quantum computing. We're talking about cracking RSA or some chemistry solutions. And you can do back-of-the-envelope calculations for how much time it takes if you know those logical clock rates. And that's very dramatic. So take this as indicative, but I think it's very telling. Now, if you want to hear more about the technology advances themselves, what's been going on with these devices over the last 12 months, which, as I've said, is extremely exciting, then I would encourage you to go to the keynote session tomorrow morning, and that's really a rare opportunity to see Professor Pascal Senlar speaking. If you want to learn about scaling smart and finding utility as soon as possible, I would also encourage you to go to Xavier Pereira's talk tomorrow, which is going to talk about scalable quantum machine learning. But let me try to wrap up, and I'm going to come back to this device. So I started out by making a fairly fantastical claim, and I hope I've backed it up to some extent here. We're working with a technology that is 100,000 times more efficient than our biggest competitors, and that's before we even start to bring in the optimizations, our native architectures, and so on. Now, I'm aware that 100,000, this is a big number, and sometimes our imaginations struggle to really grasp what that means. And so I was trying to think of an analogy. And something that came to mind was to make the analogy with Moore's law. And it's very similar, right? Moore's law says that every 2 years, the number of transistors that you fit on a state-of-the-art chip doubles. Right? It's about resource efficiency. You get more resources, it doubles every 2 years. Of course, that brings some advantages in computational power and reducing the cost and making it more accessible. But fundamentally, it's about resource efficiency. And I was trying to think, how many years of Moore's law scaling did it take for 100,000 time efficiency advantage? Well, actually, when I looked it up, you got to go for the stretch 1982 to 2020 for Apple's M1 chip. It was an Intel chip, was the state of the art in 1982, to have a 100 times scaling. And I think you can see what changed in computing over that time. So, if you care about truly useful, practical, fault-tolerant quantum computing, it's not going to be about who builds the biggest factory. It's going to be about who builds the smartest factory. And it might just be that this device that I'm holding is the key to finding the shortest path. Thank you very much.